Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from Deshbandhu College, University of Delhi. Today we are going to discuss about the module Device Applications of Conducting Polymers from the paper Functional Materials. The main points which will be covered in this module are various applications of conducting polymers. Second, organic light emitting diodes, their device structure and their advantages will be discussed. Third, organic solar cells, whose mechanism and the device structure will be explained. Fourth, the performances of different solar cells using various conducting polymers are discussed based on their efficiency. So students, let us start with a brief introduction about the module. Conducting polymers such as polypyrrole, polythiophene, and polyanilenes. They are complex dynamic structures that captivate the imagination of those involved in intelligent material research. The application of electrical stimuli can result in drastic changes in their chemical, electrical, and mechanical properties. These complex properties can be controlled only if we understand first the nature of the processes that regulate them during the synthesis of conducting polymers, and second, the extent to which these properties are changed by the application of an external stimuli. Applications of conducting polymers. So students, we have already discussed about the conducting polymers. Now we will discuss about the applications part. Conducting polymers are used in the variety of devices such as OLEDs or organic light emitting diodes based displays. Second, organic photovoltaics or solar cells, sensors, batteries, lighting, circuits, memories, etc. Out of all these applications, the first two applications, that is, in organic light emitting diodes based displays and the organic photovoltaics or solar cells, are the most important applications. Now let us discuss about the organic light emitting diodes. Organic light emitting diode was fueled by C.W. Tang's discovery at Kodak Labs in 1985. An OLED or organic light emitting diode is an electronic device in which a series of organic thin films are placed between the two conductors. Application of an electric current leads to the emission of bright light from the device, and this process is called as electrophosphorescence. Even with the layered systems, these systems are very thin usually less than 500 nanometers. So the advantages of these OLEDs are: one of the major attraction of OLED technology is they produce the display that are self-luminous, which do not require any backlighting. Second, the absence of backlighting and the components associated with it result in a very thin and very compact display. Third advantage of these is that the display, they have a wide viewing angle up to 160 degrees and requires very little power. Besides OLEDs, they also provide a high resolution to the display, bringing crispness to the eye. Now students, let us discuss about the device structure of organic light emitting diode based display. The device structure of an OLED comprises of a stack of thin organic layers consisting of the emissive active layer sandwiched between a transparent anode used for the emission of light and a metallic cathode. The stack of organic layers typically consist of a hole injection layer to facilitate the hole injection into the emissive layer, a hole transport layer, an emissive layer, the key component, and an electron transport layer. Upon application of an appropriate voltage, typically between 2 and 10 volts to the device, the injected positive and negative charges reach the emission layer where they recombine to generate light through a phenomenon called as electroluminescence. Now students, let us first discuss about what is electroluminescence. Electroluminescence, or EL, is a phenomenon in which light is generated by an electrical input. In the context of organic devices, the simplest form of an organic or polymer LED device may contain a single layer of an electroluminescent material called as emissive layer, which is sandwiched between the two electrodes, anode and cathode, for example, indium tin oxide (ITO) and calcium or aluminium respectively, which is shown in the figure below. Now, as evident from the figure, when a sufficient bias is applied to an LED device, electrons and holes are injected respectively from the positive and negative electrodes into the electroluminescent material. These injected electrons and holes then recombine within the electroluminescent material or the emissive layer, forming a neutral excited species called as exciton. The decay of these excitons to the lower energy ground state leads to the emission of energy in the form of light, while the process is radiative. The color of the emitted light is governed by the difference between the excited state energy and the ground state energy. The key in this device is to maximize the recombination of charge carriers in the emissive layer, and hence it is important to design and tailor the structure of the organic layers as well as appropriately choose the anode and cathode, maximizing the light output from the OLED device. Now let us discuss about the OLED devices. Often, single-layer LED devices also have problems with unbalanced charge injection, that is, when more electrons are injected than the holes. This results in the lowering of efficiency of the devices. To prevent this, often researchers use charge transport layers to facilitate the selective transport of electrons as holes from the respective electrode. These are called as electron transport layer or ETL and hole transport layer HTL respectively. These layers provide several benefits to the device performance. First, if there is an energy barrier between the electrode, Fermi level, and the HOMO or LUMO level of the emitting layer, these layers provide intermediate energy states, making transport of electrons or holes through smaller successive steps like energy barriers, improving the device performance and helping in achieving in low voltage operation. Second is the balance of transport of electrons and holes by proper choice of layers and their energy levels. Third, it helps in minimizing chemical or atmospheric degradation of the active either via environment or electrodes. Lastly is the minimizing losses at the interfaces between the electrode and emissive layer interfaces. Now students, let us discuss another important application of conducting polymers, that is organic solar cells. In 1986, C.W. Tang discovered that organic semiconducting materials can be used to create a p-n junction solar cell. These organic solar cells, they also have certain advantages. First, the solution processability of the key components. Second, potential prospect for lower cost of the materials. Third, relatively simpler and cost-effective fabrication processes and the potential of large area processing on flexible substrates. Fourth, availability of inexpensive and environment-friendly raw materials. And lastly, the ability to tune the molecular properties. So students, now we will discuss about the mechanism and the device structure of organic solar cells. In contrast to the inorganic solar cells, where absorption of light leads to the formation of a free electron hole pair. In organic solar cell devices, exposure of the material to the light radiation leads to the creation of an electrically neutral exciton, a pair of electron-hole pair bounded by Coulombic force of attraction. This is attributed to the low dielectric constant of organic materials, which causes the radius of the attractive Coulombic potential to spread over a greater distance. As a result, the binding energy of these excitons is quite high, often exceeding 100 MeV, and hence thermal energy at room temperature is insufficient to break these. Once the excitons are formed, they diffuse in the material driven by a concentration gradient, not by the electric field as they are electrically neutral, until they recombine or they dissociate to form free charges. Since the exciton diffusion lengths are shorter in organic materials, which is of the order of 10 nanometer or so for a typical material, we ideally require the exciton dissociation sites to be located close to their formation site. Exciton dissociation is generally brought about at the regions of high electric field, such as interfaces like the organic-organic interface or metal-organic junction. It is because of this lack of exciton dissociation sites, single-layer organic solar cells have an inherently low efficiency. To improve power conversion efficiency of these cells, several new structures like the bilayer devices, bulk heterojunction, and tandem cells have been proposed, and they are implemented where one can use a thickness layer of materials, say up to about 100 nanometers, so as to be able to absorb more light whilst not losing on the number of dissociated charge carriers. A typical organic solar cell consisting of an active layer sandwiched between the cathode and the anode is shown in this figure. Active layer is the organic layer, which can be a single layer, a bilayer, or a bulk heterojunction layer, or some other structure based on the type of solar cell being fabricated. One of the electrode is typically transparent to allow the light to follow upon the active layer. So in this case, we are using the ITO coated glass, from where the light is allowed to fall upon the active layer. Excitons, which are formed upon the absorption of photons, are dissociated into the free electron hole pair and are then transported to their respective electrodes by hopping mechanism. This figure shows the entire solar cell operation from the absorption of light to the generation of power. So students, this whole process you can see is divided into 5 steps. As mentioned earlier, organic materials have a very high absorption coefficient, and as a result, a thin film whose thickness is less than 100 nanometer of these molecules is sufficient to absorb most of the photons falling on it. The range of absorbed photon energies is determined by the absorption spectrum of these molecules. Each absorbed photon causes an electron to be excited from the HOMO level to the LUMO level and thereby leads to the creation of an exciton. The exciton formed is electrically neutral and its transport is not affected by the internal electric fields. Instead, it moves by diffusion, hopping from one molecule to another such that the probability of each jump is maximized. These excitons can either recombine radiatively or non-radiatively or can dissociate to give free electron-hole pair. This is shown by the third step in the block diagram. To increase the probability of dissociation, time constant for dissociation must be smaller compared to the recombination rates. Thus, to minimize the probability of recombination, we want exciton generation to occur close to the dissociation sites. Sharp potential drop at the organic-organic interface forms an ideal dissociation site. Charges created by generation have to be transported to respective electrodes. This is shown by the fourth step in the block diagram. The electrons are transported via an electron transport layer ETL by hopping to the cathode, while the holes are transferred via hole transport layer HTL in a similar manner to the anode. The built-in electric field or drift current and the charge concentration distribution in the material affect the transport of free carriers in the device. The electrode metals are so chosen that they form an ohmic contact with the active layer to ensure efficient collection of the charges. The cathode work function is chosen closer to the LUMO level and anode to the HOMO level. While selecting the electrodes, one of them is generally chosen to be a transparent surface or substrate so that the incident light can reach the active layer. The electric current that a photovoltaic solar cell delivers corresponds to the number of created charges that are collected at the electrodes. This is represented by the final step in the block diagram. This number depends on the fraction of photons absorbed to form excitons, that is eta absorption, the fraction of electron-hole pairs that are dissociated from these excitons, that is eta dissociation, and finally the fraction of separated charges that reach the electrodes, that is eta output. Thus, the overall photocurrent efficiency of the device is given by eta total is equal to eta absorption multiplied by eta dissociation multiplied by eta output. The fraction of absorbed photons is a function of absorption spectrum and coefficient of the material, absorbing layer thickness, and the internal multiple reflections at metal electrode or the organic-organic interface. The fraction of dissociated electron-hole pairs, on the other hand, is determined by whether they diffuse into a region where charge separation occurs and on the charge separation probability. Now students, we have discussed about the organic solar cell. Now we will discuss about some of the performances or compare some of the performances of organic solar cells based on their efficiency. Due to much higher light absorption and improved exciton dissociation efficiencies, the active layer of OPV devices is the blend of two organic semiconductors, typically using poly-3-hexyl thiophene P3HT for the hole transporting material, an organic semiconductor, and 6,6-phenyl C61 butyric acid methyl ester PCBM, a soluble fullerene as the electron transporting material. The thickness of the blend layer is typically around 100 to 150 nanometers. P3HT is a widely used polymer in OSC due to its good stability, optical and electrical properties. P3HT has a band gap of 1.9 electron volt, and when it is combined with P60BM, its efficiency becomes 4%, which was reported by various groups and is still a workhouse material. The peak efficiency offered by P3HT PCBM blend is limited by their absorption being below 600 nanometer, limiting their efficiency to 5%. The other promising candidates for the OSC device performances are, that is the organic solar cell devices performances are, carbazole benzothiodiazole copolymers, second, diketopyrrole DPP based copolymers, third, benzodiethiophene BDT derivatives, fourth, indacino-diethiophene IGT based copolymers. These copolymers combine electron-rich segment with electron-deficient units, like DPP, along the polymer backbone. By selecting electron-rich comonomers like thiophene, fluorite, or carbazole-based units, we may alter the optical band gap, energy levels, and carrier mobility of the resulting copolymers. Light absorption of low band gap polymers goes up to IR region, and in combination with the fullerene derivative, they are able to absorb in the visible and UV region as well. So, this table shows some of the low band gap polymers and their highest reported efficiency. In copolymers, based on benzodiazepines (BDT) and the thionyl-3,4-B thiophene unit reduces the energy band gap of polymers. Also, it makes the polymer to be soluble and oxidative stable. The rigid backbone provides the good hole mobilities. Devices based on PTB7 have exceeded the efficiencies over 10% for single-junction devices. Till now we have discussed about the organic light-emitting diodes and organic solar cells. So students, now we will be discussing about the challenges and the future outlook of these devices. Whilst organic conducting polymers have shown tremendous promise with their commercialization in the display-related product of small area such as mobile phones, the major problem with the commercialization of these devices is their sensitivity of conducting polymer to the ambient conditions. They tend to react with the species such as moisture or oxygen, and the condition is particularly aggravated in the presence of sunlight. Whilst the life of OLED displays can be tailored to applications where product life is shorter, such as mobile phones, for organic solar cells, the requirement of having high efficiency and stability in the same material is a primary prerequisite for its commercial success, especially when silicon-based solar cells shows a lifetime of more than 20 years. The stability issues have become quite important in the case of organic thin-film devices, where device components, primarily the active layer materials, for example, the organic conjugated polymers or small molecules, are more prone to the environmental degradation, presumably due to exposure to oxygen, moisture, and light. The degradation of such devices is often controlled by the factors such as type of the electrode material and other layers. The mechanisms could be physical, for example, described by the changes in physical conditions of the device, and chemical, that is described by chemical reactions and are often categorized as intrinsic or extrinsic as well. Typically, intrinsic degradation implies degradation due to material alternations, such as changes in the morphological states of stacking layers and interface modifications due to inherent thermal characteristics of the active layer materials, while extrinsic degradation is typically triggered by external factors such as water, oxygen, and the type as well as the dose of radiation. While intensive research has been carried out to understand the degradation mechanism of conducting polymer-based devices, concurrently there have been studies to improve the stability of them. These methods include our interface modification by the use of materials which lead to stable and less corrosive interfaces, use of rather stable polymers and electrodes, different device architectures, alternative buffer layers, and carrier selective layers, as well as improved encapsulation methods. While OLEDs have made great strides, the research is still continuing on the polymer-based devices. Regarding organic solar cells, the Achilles heel is the stability problem and the low efficiencies of most polymers when scaled up. However, researchers are working on these issues and it is expected that organic solar cells will be commercialized shortly. So students, let us summarize what we have learned in this module. Firstly, the organic light emitting diodes were discussed, which offers very high brightness and low power consumption, and they are a very good prospect to make flexible displays. Second, organic solar cells are also exciting due to their potential easier method of processing based on solution processing, eventually lowering the materials and the processing cost. Second, the advantage in terms of the flexible and lightweight solar cell devices which have substantial market. Thirdly, however, the commercializations of these devices is restricted by lower lifetimes of conducting polymers due to environmental degradation. Lastly, it requires substantial research in the area of the device encapsulation that can make devices impervious to the environmental conditions. Thank you.